I think we were in the middle of the revised simplex method, and I had to quit because we ran out of time. So let me just finish that up. What step are we at? Number 1 was written up. Number 2, was it written up? You don't have it. Anyway, let me begin with number 1. Okay, I'm not finished yet. Well, we're just about finished. Let me also write down the last statement. Go to 1. That's the last statement here. If we focus on the left side portion of the board first, using the camera, maybe you can focus on here. If you're finished with writing the algorithm, let's just go through it. We've got the elementary matrices, which are identical to the identity matrix, except that you have a eta column. The eta column that we talked about is defined by the pivot element and the yk vector of the entering entering column. So we assume we're in the ith iteration. At the beginning, we assume we began with the identity matrix as the initial basis. So at the end of the ith iteration, we will have stored the elementary matrices E1 through EI. And of course, you don't really have to store all these matrices. What you store is, you just store the bad column, the eta column, or the column number for the eta column for each elementary matrix. So you need a position index, just a single number. And you just store the eta vector. That's enough for knowing what kind of an elementary matrix you have under consideration. Okay? All right, so with that, if the new basis is, say, B, we know B inverse is the product of all these elementary matrices. That's that we discussed before. So the current basic solution will be B inverse B, but rather than using B inverse, of course, what we have is we're using the product of EI through E1, that's your B inverse, times B, okay? But in carrying out this computation in a efficient way, what you do is you already have this information from the previous iteration. So you simply multiply this. This is a multiplication of a given vector by EI, which is easy to do because I showed you how to carry out those computations. There's a post multiplication and there's a pre-multiplication. So you use whichever one is appropriate in carrying that out, okay? So you just compute that. It's not really a multiplication. It's just much simpler than that, actually, if you just look back to the previous notes. So once this is available, then you go with the reduced costs. Now, to compute the reduced costs using the product form of the inverse, first you compute your W, which is CB B inverse. And to compute W, you use again the formula. It will be CB times the inverse defined by E, the product of all these elementary matrices. So you've got the formula here. But how do you carry out the actual computations? This is CB times EI. So this is the first one you do from the innermost. And then you do whatever you get a vector here. Then again, you multiply that vector with the next or the penultimate, the elementary matrix. So that's the second one. So on and so forth. So finally, you multiply it with E1. All right, so all of these are, if you do one at a time, they are very efficiently doable. Okay, that's the idea here. And once you've got your Rn, well, once you have W, of course, this will be Wn minus Cn. It's just a regular matrix multiplication here. So if Rn happens to be less than or equal to 0 in each component, then fine, you're done. That's the optimum solution. Otherwise, there's a Rj, which is positive, in which case this is for a minimization problem. So we continue with the next step, step 3. In that case, you identify some variable xk whose reduced cost is positive. That's an entering variable. Suppose that's xk. And once you have xk, of course, you compute yk, which is b inverse times the original ak column for that. And how do you do that? Yk is, again, b inverse, which is the product of all these elementary matrices, times ak. Okay? If you forget the parentheses, of course, it's just b inverse times ak. That's what it is. But the parentheses tells you in what order you carry out these actual computations. The first one is the innermost, second one, so on and so forth, up to the last one. Okay? So the order changes between that one and this one. Here, from last one towards the first one. Then here, you go from the first one to the last one. Okay? And once you have that, then you've got the yk vector. You compute your usual ratios of the current values of the basic variables divided by the positive elements of the y vector. Of course, this is only for yjk that are positive. Okay, these are the ratios. And then that tells you, well, one of the minimizing ratios tells you which variable is supposed to exit. And, of course, it also tells you what the pivot element will be. Okay? Once you've got the pivot element, you can define your new elementary matrix using your new eta vector. And then everything is recycled. In other words, you go back to step 1 and just carry out all these the computations one more time. Okay? I hope that's clear. I'm not going to give you an example for this. The ideas are Actually, the first example I gave you, things were done in essentially the same way, except that everything was done in pivoting form rather than using elementary matrices. This is just an alternate way of computing the entire stuff. There are also other methods to carry out these computations more efficiently in computers, such as using LU decomposition, etc. But I'm not going to go through them. But in the exam, you never know. I may ask such a question and you figure out what to do, okay? You never know. Because these are, once you've got the main ideas, you should be able to work out such things on your own, actually. That's the idea here. Don't memorize stuff. Understand. That's why it's more important to get the essentials ingrained in your mind, and then you should be able to work out many of the other details. Okay. So now what I'm going to do is I'm going to continue with simplex method for bounded variables. New stuff. I think it's quite warm here, don't you think? Maybe we should open a window. Huh? Why don't we open that, Bilal, also? Yeah. Emre, yes. It's too much. Now let's look at a problem of the form minimize Cx subject to Ax equals B, standard form. Except that rather than having x non-negative here, we have a lower bound vector L and an upper bound vector U, giving you bounds, lower and as well as upper bounds for each of the variables. Okay? Again, I'm going to assume A is m by n, and rank A is again assumed m. And so we have n variables. Now, if you use a regular simplex method, first of all, you don't have the usual non-negativity here. So, but the simplex method, typically we worked it out for the standard form problem, which has Ax equals B and non-negativity. Of course, plus the additional constraints, the upper bounds. So you might want to simply transform this into the standard form, into something that looks more like the standard form, with non-negativity. How would we do that? We can make a change of variable. We can define, say, x prime to be x minus L, which means that you're subtracting the lower bound vector L from here, from here, from here, as well as here. If you do that, x prime will be bounded below by 0 and above by u minus L. Let's call it u prime. So that's by definition equal to the original u minus L. Of course, we assume u is greater than or equal to L. Otherwise, you can immediately conclude that this is infeasible. Okay? All right, if you do this substitution, the problem transforms into minimization of Cx prime subject to A times x prime equals B plus something else. Yes, minus or plus? Minus A times L. So let's just call that B prime.
No, plus.
Is it plus?
Minus
Yeah,
L,
it's plus. So B prime will be actually equal to the original B plus A times L. X minus L, yes, okay. And x prime will be less than or equal to u prime, and x prime will be greater than or equal to 0. In this case, of course, you can add slack variables here to transform them into the usual format, the standard form problem. So if you add a vector of slacks here, say S, and also require S to be greater than or equal to 0, so this becomes, with slacks, x prime plus S equals U prime. So everything is in just about standard form. Now, if you want to work out with this form, how many constraints do I have here? The original constraints are m, and then you've got additionally n constraints. So you've got m plus n equality constraints. And how many variables? I don't know. N plus n, 2n, yes. So both the column space has been enlarged as well as the row space is enlarged. Okay? And of course, your simplex tableaus, if you work with the regular simplex method rather than the revised method, it will have m plus n, so simplex implementation. Basis matrices will be m plus 1, m plus n by m plus n. So it will have m plus n rows plus the row 0, the additional row. And you have how many columns? 2n columns. Plus the decoration column for z. Plus the right-hand side column, but I'm not worried about those. So the row space or the number of rows is too large. Okay? So this is not recommended, although it's doable. Rather than working with a basis of m plus n by m plus n, we want to work with a basis of m by m. So we want to extract a basis directly out of A matrix, rather than doing all these transformations, etc. So the question is, how do we work out the details of this? So here's the basic idea. For an extreme point, how many binding equations do you need? You need n equations. Okay, so m of them will come from here. And then you've got inequalities of this form, and then also inequalities of the form x greater than or equal to L. Okay? So you need a total of n minus m equations from this part. Except that, of course, those n minus m may be distributed in different ways to these inequalities. So, for example, say n1 of them might come from here, and n2 of them might come from here. Let me change this to n2m, n1. It's better that way. Okay. So you want to make sure that n1 plus n2 is equal to n minus m for an extreme point. Of course, they should also be linearly independent. That's the other condition. And so here, the variables that are going to be taken as equalities or at their bounds, those are going to be the active constraints, and they are going to be your non-basic variables. Okay? Remember that in the usual case, when x is just bounded below by the 0 vector, the non-basic variables are those variables that are taken to be 0, which means they are taken as active constraints. Here, the same thing. Non-basic variables are those that are at one of their bounds. some n1 of them will be at the lower bound, some n2 of them will be at the upper bound, and the total will be n minus m. And the remaining variables will be your basic variables. Okay? Of course, you want to make sure that the non-basic variables that you choose are such that when you have the equality for those variables, and just ignore the remaining ones, the ones that correspond to basic ones, you have n equations here, m coming from here, n1 plus n2 coming from the remaining part with equalities. And that equality system has as many variables as you have equations. Okay? And then you want a unique solution there. In other words, they should be linearly independent. So, which means that for the remaining ones that are not taken at their bounds, you have to solve for them. Okay? And to be able to get a unique solution, again, we need to have the columns of A corresponding to the basic variables. They should be linearly independent. Okay? That was the situation with the old stuff, and it is the same situation here. The active constraints taken in this way are linearly independent if the basic variables or the columns associated with the basic variables or the variables that are going to be solved for are linearly independent. So we're talking about an m by m basis matrix. So that's how you get your basis matrix. The columns associated with the basic variables will give you the basis. So, suppose we have a basis B consisting of some m linearly independent columns of the A matrix, and these columns are the ones associated with the m basic variables under consideration. The remaining variables, how many of them? N minus m variables are at one of their bounds. And they are the non-basic variables. Okay? So, partition the variables in such a way that so let's partition A into the form basis matrix N1 and N2 rather than just a non-basic one, where N1, one of them corresponds to lower bounds, the other one corresponds to upper bounds, but which one is which, I don't remember, so let me just check that. Yeah. N1 will correspond to the lower bounds. Yes, I said that, but I wasn't quite sure when I said that. So, yes, that seems to be the case. So, the variables are also partitioned into subvectors. Xn sub 1 houses those variables that are set equal to their lower bounds. So you just identify the lower bounds associated with those variables, and that's your subvector, L sub n1, coming from L. Okay? And so that's a particular solution. Let's just mark it as bar. And Xn2 corresponds to another subvector of variables. Of course, these are disjoint, where they are set equal to the upper bounds. And these are altogether non-basic. And what else do we have? We've got the basic variables, but we don't know what they are. So we should solve for them. They are unknown right now, or to be solved for. Okay? So how do we solve for them? Well, we just rewrite AX equals B in the form BXB plus N1 XN1 plus N2 XN2 equals B. That's the equality portion of the constraints. And of course, we're talking about the particular solution. So we've got bars here. And that, of course, tells you that XB is equal to B inverse into B minus N1 ln1. I'm just substituting the lower bounds and upper bounds for the respective variables, N2 UN2. And so XB will be equal to B inverse times the entire thing. Okay? Let's call this B cap. So XB is equal to B cap. The other ones are as given. Okay? That's the situation. Now, this is so your basic solution is the vector x bar specified by the boxed portions here. Okay? Lower bounds, upper bounds, and B cap as dependent on the other variables. Is this a basic feasible solution? Not necessarily. This basic solution is basic feasible if B cap is between the upper bounds and lower bounds associated with the basic variables. Of course, this is your XB here. Okay? So if XB is also between the bounds, fine, you have a basic feasible solution. If not, you don't, then of course you don't, in that case, you don't really want to deal with that. You want to begin with a feasible basis and then continue with your simplex iterations, ensuring that the new basis matrix is always feasible. Okay? All right. So what is the objective value? So let's assume that somehow we ensured B is feasible. Assume B is a feasible basis. What is the objective value corresponding to this, the Z bar value? Well, it's going to be CB, B inverse, well, no, CB XB. Let's just write down the proper form here. Cn1 xn1 plus Cn2 xn2. That's your objective function value with specified values for all variables. Now, if you rewrite this, this is going to be CB times XB bar, which is B cap, plus C n1 ln1 plus Cn2 un2. Okay. Now, this tells you what the objective value would be as corresponding to the current basis or the basis on hand. But it doesn't quite tell you how to move from this basic feasible solution to an adjacent one, which improves the objective value. Okay? So in the simplex method, you are looking for an entering variable, and that's what you need to do. How do I define adjacency here? As in the old case, in other words, the new basis or the new basic feasible solution will be adjacent to the old basic feasible solution if some non-basic variable is now basic and some basic variable is now non-basic. Okay, so a swapping of the roles again. The question is, how do I identify which non-basic variable should become basic now? So Z is equal to CB XB plus Cn1 xn1 plus Cn2 xn2. Now, I'm not taking any longer xn1 and xn2 to be the specific values that we take them to be, okay? In other words, I want to investigate the objective function value for any choice of the non-basic variables if you allow them to become different from what they are currently, okay? For that reason, of course, things will be this way. Now, xb as dependent on xn1 and xn2 is going to be how much? As you would see here, except that rather than having L and U here, what do you have? You have xn1 and xn2. Okay, so CB times B inverse times B minus n1 xn1 minus n2 xn2. That's your xb as dependent on x. Why do I make it this way? Well, this ensures that you satisfy ax equals b. That's the only way you can satisfy that. Okay? Plus cn1 xn1 Cn2 xn2. So xp should be taken exactly the way we defined in the b inverse times the parenthetical part to satisfy the ax equals b constraints. Okay? You just simply solve for xp using these constraints. That's it. Did we do it right? Yes. We did it right. Yes. Mm-hmm. Okay. So if you simplify this, what do you get? You get CB B inverse B yeah CB B inverse B minus something times xn1 here minus something else times xn2 here, which is not really difficult to compute. What are the multipliers for xn1?
CB minus 1 minus Cn x1.
CB B inverse n1 minus Cn1. Yeah, that's your multiplier for xn1. For the second one, of course, we have something similar. CB B inverse n2 minus Cn2. That's it. And of course, you can see that this is your definition for the reduced costs associated with the non-basic variables that are at their lower bounds. And the other part is also similar. This is the reduced cost vector for those variables that are at the upper bounds. Now, this value is not quite what you want here. You would rather have z cap there. Nevertheless, don't worry about that. Assuming that these are the reduced costs, what we have here is a constant minus summation. This is the reduced cost row vector times the column vector xn1, so it's just a dot product, rj xj, where j is, say, restricted to set of indices r1 minus summation rj xj, j restricted to set of indices r2, where r1 is the set of indices j for which xj is at the lower bound, and r2 is the set of indices j for which xj is at the upper bound. Okay? So we partitioned the non-basic variables into two subsets, those at the lower and those at the upper bounds. This is the situation. Okay. So here's the question. If I want to improve my objective function value by an inspection here, this is what you've got for z. How would I do that? Now, we're minimizing. This is for minimization. So if xj is at the lower bound, and if I increase it from the lower bound, and if rj is positive, then this will give me a reduction in z. Okay? It will make it go down. On the other hand, there may be variables here in the second part. If Rj is at the upper bound, then you can decrease it actually from the upper bound. When you decrease it, you want a negative Rj here so that the overall contribution is again a downhill or a decrease in Z. Okay? So, hence, if Rj is positive for some j in R1, then Xj may enter or can enter to improve the objective value. And if Rj is less than 0 for j in R2, then Xj may also enter. Okay? So depending on which index set you're looking at, you either look for a positive reduced cost for lower bounded variables, and you look for a negative reduced cost if the current non-basic variable is at the upper bound. So things will be a little bit more complicated. So let's see. Problem set number 8. Chapter 3. Plus, maybe you might also want to look at 34, 40, 46, 50, and 51. This is optional. All of them are optional, but this is more optional than the other one. Okay. Chapter 4 is for finding an initial basic feasible solution, you know, the big M and the two-phase method. So you need to look at these problems. Chapter 5 is for revised simplex method, degeneracy, etc. Okay? The cycling stuff, etc. Okay. That should prepare you well for the exam. I hope. I think we were in the middle of the revised simplex method, and I had to quit because we ran out of time. So let me just finish that up. What step are we at? Number 1 was written up. Number 2, was it written up? You don't have it. Anyway, let me begin with number 1.